introduce Professor Ashutosh Trivedi. So Ashutosh did his PhD in 2009 from the University of Warwick, where along with things that they do in UK like tea and scones, he also got his knowledge of automata theory and logic and programming languages and such things. And then he went to Oxford University in the UK and to University of Pennsylvania as postdoctoral researcher for a few years. And then he had a long journey across the world, globe to Indian Institute of Technology, Bombay, where he was a faculty member for 3 years. And then he decided to come here as a research faculty to help us out on a large DARPA grant, where he literally led the grant and did so much for us over a course of few years that we were super thrilled when he expressed his interest in joining us as tenure track faculty. And so in 2017, he joined us as a tenure track assistant professor. And now you will hear about what he has done since then. So over to you, Ashutosh.
Thank you, Shriram. Am I audible in the back? Can you hear me? Right. So thanks, Shriram, for this wonderful introduction. It's nice to be introduced in your own university, right? So I'm super excited to talk about some of the recent work which has been going on in our group on making reinforcement learning or in general AI more programmable, more accessible, right? And safe by developing different programming languages and verification tools to support our programmers, right? Let me just quickly see if I have the slider on the right place. Okay, so the pitch here is that each and every one of you present here today, right? We care deeply about developing high quality software system, right? Software systems which are safety critical. These systems could be safety critical, security critical, business critical, societal critical, right? And in our different groups, we have expertise in developing, high quality software systems, hardware systems, or cyber physical systems, right? Based on principal technologies like formal methods, software engineering, programming languages, right? To kind of develop these kind of systems with high accuracy and trustworthiness, right? But recently we have been witnessing a trend in programming. More and more our programs, right? They have this kind of learning components inside, components that are trained using input and output data, components that have, learning agents inside that interact with the environment, and as they interact, they change their own code, so to say, right? So while we are confident in developing traditional systems, how can we help our programmer to develop this new kind of systems which are learning enabled? So this change in status quo in programming has come because of the recent marriage between these two technologies. On the left, we have reinforcement learning. These are the approaches that interact, where you have a learning agent that interacts with an environment, and with each interaction, it kind of gets some of the rewards, and based on those rewards, it kind of maximizes, those sequence of rewards and learn an optimal behavior. And on the other side, you have deep feed-forward neural network. These are like this general purpose approximation architecture that could learn, highly nonlinear function from input-output data. But something interesting happens when you combine these two approaches, and you get something super powerful, right? You have this deep reinforcement learning that not only can kind of Okay, and we are back now.
And then you'll want to share your screen.
Oh, you want to share the PowerPoint?
Yeah, I will do that there.
Okay.
Okay, so sorry about that. I think we are back, hopefully over Zoom as well, right? Okay, as a consequence, deep reinforcement learning is increasingly being applied in different programmatic applications, right? In particular, we are using that in two different settings. The first one is program synthesis, where where a programmer kind of writes a sketch of the program, and the reinforcement learning agent sort of interacts with an environment, right? And learns how to fill those holes, right? And another setting is kind of slightly more kind of exciting, which is adaptive program, in which you have a programs that themselves, they have these learning components inside, right? And as they interact with the environment, they continue to modify themselves based on changing requirements and the distributions. So the goal of my research is to kind of seamlessly integrate these learning components inside the programming workflow, right? And in particular, by looking into these systems where you could write the choices available to agent as a program, you could write your environment as a program, right? And you can even write the reward system as a program. And we would dub this setting programmatic reinforcement learning, right? So here is kind of a quick mock-up of how programmatic reinforcement learning looks right now, and what are some of the pain points in the current approach where we would like to help programmers to improve their life. So the current interaction of programmatic reinforcement learning starts where a system programmer, so to say, right? It initiates the programming by defining what is an environment for the reinforcement learning agent. That could be an arbitrary program. In addition to that, your programmer specifies what are the different rewards for the reinforcement learning agent, right? The second step is, because the environment in general, especially for programmatic learning side, it could be general programs full of your programmatic abstractions like subprograms, subroutines, modules, and so on, right? Now programmer is supposed to kind of find features, interesting features in the environment, so that it can kind of expose them to the reinforcement learning architecture, right? So programmer has to find what are the interesting features, what are the approximation architecture to be used in this setting. Once these components are specified, reinforcement learning agent then can go on, interact with the environment, and based on the reward, continue to maximize those reward signal. And as a result, it computes a program, right? So let's see what are some of the pain points in this setting, right? I would kind of start with the usability pain point. You see that the biggest kind of challenge in programming these systems, because it's reinforcement learning, right? The problem here is that the programmer can only interact with such a system in the language of reward signal, right? We as humans, we don't think in terms of reward signals. We think in terms of higher level logic, programs, right? Natural language. And this is kind of quite a straitjacket when you have to program these systems, because now humans, they are forced to think in an assembly language of sorts of programs. Second step is, now the humans, they are supposed to be an ML expert in identifying what are interesting features, right? Once you find those features, you have to manually find what is a good approximation architecture. Once that is done, so these kind of two components, they bring some of the usability challenges. On the other hand, something interesting about scalability as well, right? Every time you think about deep reinforcement learning, you would say, well, this should scale really well, because we have neural networks, we have machine learning. These technologies are known to scale, right? But then there is something interesting happens in this context, right? Because you have this general program as an environment for reinforcement learner, right? You cannot directly feed this discrete infinite state space essentially to the reinforcement learning agent, and programmer has to find some kind of a flattening of that state space as a kind of interface to the reinforcement learning, right? So all of the modularity which was there present in the program is completely lost to the reinforcement learning agent. And that's a big problem with respect to scalability. Finally, there are multiple challenges with respect to trust, right? The number one challenge here is, because our human programmers, they are programming using this scalar reward signals, right? There is no And this kind of programming happens sometime, under time pressure and so on. And it's kind of very difficult to verify whether you're not doing the garbage, garbage in, garbage out, right? You have some mental specification, but you're forced to write these scalar reward signals, right? That's one of the lack of trustworthiness, starts from there. Second component is, of course, feature selection is a big thing, right? It's again manual, again error prone. Finally, once you have a program, right, it's difficult to verify also because you don't know your specification to start with. These were given as a reward signal, and essentially because you don't have the specification, you're not able to use this, formal methods or other approaches to kind of software engineering to kind of, rigorously test the correctness of your program. So the goal of my, the vision of mine and is to kind of look into principled methodologies and powerful tools to improve these three aspects of reinforcement learning, right? Usability, scalability, and trustworthiness. I'm super lucky to have a really clever set of students. All of them are sitting in this row over here, right? To help me in this vision by developing these methodologies and tools to support this idea. Okay, so let's see what we'll see in the talk today, right? We would have essentially from these three kind of dimensions, we'll choose three interesting ideas and talk more in detail about that, right? The first part we would discuss today, in the first part of the talk, we'll talk about programming language of rewards. Later on, we will introduce this idea of recursive reinforcement learning, right? That generalizes reinforcement learning from your finite Markov decision processes to MDPs that could have, arbitrary program invocation inside, right? With no restriction on recursive nature of that, unlike the current state of the art of hierarchical reinforcement learning. Then we would look into some of the safety critical systems and what is kind of a model of, developing safety critical systems using reinforcement learning. In particular, I'll talk about next generation cardiac pacemakers and what is the role of learning when you have to design such devices. Finally, I would talk about some of the current and future directions. In particular, we'll kind of quickly touch upon some of these issues beyond safety critical systems. I would talk about security critical systems, some of our work on fairness, improving fairness of such systems, right? And we'll talk about some of the exciting work on how to develop accountable systems, that is systems which have legal criticality attached to those. Okay, so let's get started. In the first part of this talk, I would talk about some of our work on improving usability of reinforcement learning, in particular by developing programming language of sorts for rewards, right? Before we do that, let's understand what is reinforcement learning quickly, right? Reinforcement learning is this sequential decision, optimization approach to sequential decision making, where a learning agent interacts with an environment in episodes, and with every interaction, it gets some feedback from the environment in the terms of reward signal. This learning agent is essentially trying to maximize the sequence of those reward signals. And in doing so, it learns the intended objective, which was inherent in the reward signals. So let's take one of this example. You may already have seen this frozen lake example. We have this, 4x4 grid of sorts. Then you have reinforcement learning agent with finitely many actions, north, east, west, and south, right? At every step, you are in a particular state. Your reinforcement learning agent is in some state, chooses some action. Based on that action, observes what is the next state, and observe also the reward signal connected to that. And this interaction continues, right? So from the next state, it would choose again some action. Based on that, observe the next state, corresponding reward, and so on. And once you kind of finalize this, finish this episode, and there would be many different ways to stop the episode, right? It kind of uses this sequence of rewards to maximize, the choice of actions based on approaches like dynamic programming. Just to get a quick idea on reinforcement learning, there are two flavors of reinforcement learning, right? First one, which is known as model-based reinforcement learning, where you have this learning agent that interacts with the environment, right? And as it is interacting, it's trying to construct a model of the environment, right? a formal mathematical model for that is this Markov decision process. Finitely many states, actions, and actions are probabilistic. Once you have learned to certain accuracy this model, you could use approaches like linear programming, value iteration, and so on, right, to compute optimal policy. So that's nice. Another version of reinforcement learning is this model-free reinforcement learning, right? The good thing about this kind of approach is that it's more space efficient, asymptotically more efficient than the other approach. And in particular, you're not trying to learn the whole model. Here you are trying to only understand what is a different, quality of different actions from different state. And you could use this quality in a tabular format. And in particular, you could use neural networks to summarize that table, right? So essentially, kind of a quick connection is model-free reinforcement learning is like foundations for deep reinforcement learning. So now one could think of reinforcement learning is this kind of as a programming paradigm with scalar reward, right? You have the whole act of programming reduces to finding rewards in different states, right? So now you have to say in some particular state, choose an action A, you get a particular reward of 0.5. In some other state, it is 79, right? And this is like a interaction that you would have with your reinforcement learning agent, right? So now with this kind of interface, programming interface, reinforcement learning is in the same place where programming used to be before we developed high-level programming languages, right? You are programming in the language of assembly language of rewards. You would say, Ashutosh, maybe I'm very good into these things, right? I know how to give rewards nicely every time, right? So I agree with that, right? Some of the rewards are super easy to express. Like we have seen this, frozen lake example. Every time you have reached your goal, you give a reward of 1. Otherwise, you would give a reward of, -1 to kind of promote this speedy learning. On the other hand, sometimes this could be particularly challenging how to give rewards. Right. So let's look into this setting. It's again grid world example. We are given 4 different grids, 0, 1, 2, and 3. And you could see different actions over there. For example, if you start from grid 0, you could choose action A to go to grid 3. You could choose action C to come back, and you can make that loop of A and C forever, right? Or you could choose action B, which seems to be a probabilistic action. With some probability, you would go to green cell. With some other probability, you go to the blue one. Right here, I want to kind of think about green is good and blue is bad, right? Imagine your objective is the following. You would like to always avoid visiting blue region, right? And you want to infinitely often visit the green region, right? That's your specification. And you're a programmer, you want to give rewards for that. And what's the most intuitive reward in this case? You would say green means something good, so I'll give a reward of something positive. Blue is bad, I would give a reward of negative, right? And that's seems to be most intuitive reward in this context. But you would see today that this reward is kind of, is wrong really, right? And we would understand how to provide a proper reward for this setting. And at least I'm hoping that this example would kind of, convince you that it is quite challenging to directly program in scalar rewards. One thing you would like to notice from this example, it's possible to satisfy this property, right? I hope you could all of you could see what is the optimal behavior in this case, right? You will start from 0. You could choose an action A to go to green, action C to come back. If you do that forever and ever, you satisfy your property. Great. We could write properties like this in formal logic, right? There is this logic, linear temporal logic, which is logic of, traces, where you could talk about infinite traces of the system, thinking of, linear temporal view of that sequence, right? So you could say things like globally not B, right? And so G not B, globally don't see a blue region, and GF globally eventually, that every step, sometime in the future, you keep on seeing the green. In that sense, you are seeing green infinitely often, right? Good thing about this kind of fragment of logic is that it could be automatically compiled into a monitor automata, right? So it's like this monitor automaton is like your DFA, but slightly more subtle. Instead of looking into finite traces, it reads infinite sequence of traces, right? And accepting sequences are those which would see these accepting transitions infinitely often, right? So quickly check it out, really this property matches with this gadget or not. Essentially, every time you would see a green region and not a blue region, you would take this transition. Every time you see a blue region, you can go to a trap and hence would never be able to satisfy this specification because you would never see green transition infinitely often, so to say, right? So hopefully that kind of automata gives you that kind of a connection between the two. How do we use this logic? Let's say it's a restricted language, but let's see how do we use this language in reinforcement learning. So let's take our example. We could write the corresponding MDP. It's like a more friendly picture. Essentially, both of these pictures are the same, right? Here, I would like to kind of quickly show something here that you have different states. And I'm kind of writing also some of the predicates over those. What is the quality of that? It's a green region, it's a blue region, and so on, right? So now you have the following situation. You have an environment which is not known to you, right? And stochastic as well. You have a learning agent and you have a specification that is given to you in some kind of a gadget now that has been automatically compiled from a higher level language. How do we use this logic in reinforcement learning, right? Again, there are two flavors of this reinforcement learning. The first one could be model-based reinforcement learning, has been around since '85. The key idea here is that you would, after you would learn your system to certain confidence, you have your monitor gadget, you can take these two objects really and take their synchronous product of those two, right? You could trust me that this kind of synchronous product of those mathematically defined to be this particular object, and the whole problem of finding a policy here that satisfies that objective with maximum probability kind of reduces to finding a policy in this particular object where you would see these green transitions infinitely often, right? In other words, all you have to do is find an end component of this where you would, you could stay forever and you could continue to visit green transition and you want to maximize your probability. Quickly check that again. If we didn't lose anything in the translation, you could choose A and C forever and ever and satisfy the property with probability 1. Okay, let's understand the other part of this, right? Model-free reinforcement learning. How do we go about it, right? And there has been some work in the past which kind of try to translate this particular fragment of logic to rewards. And it's so tricky that, I mean, a lot of people, they got it wrong before us, right? So let's understand what used to be the specific reward translation before we talk about our own. So you have reinforcement learning agent, you have a monitor. Every time it chooses some action, you would see a sequence of observation, essentially, like yellow, green, and so on, right? You have an interpreter that would execute that sequence over the monitor. And in doing so, you would see like, non-accepting, accepting, non-accepting, accepting transition. And what is most logical is to take accepting transitions, something good is happening there, give a reward of 1. Unfortunately, this simple reward scheme is incorrect. And we have shown kind of the bug inside that. I would kind of quickly try to talk about what is the problem with that approach, right? And that goes really deep down in kind of our confidence in we could, write the reward all the time, right? And then we would see how to fix that. So this particular example, let's go back to our example. We would look into this kind of a simple cross product that we have seen before, right? And take my words for that, the optimal policy, right, that maximizes, the logical objective with this particular reward scheme has been reduced to an average maximization, right? So you would see at every green step, you will get a reward of 1, or every kind of accepting transition, this green dotted 1, right? Otherwise 0. So this reduction would say, sorry, my kind of pointer is not really clear here, right? But you would see that you have, once you reduce the problem to this average maximization, you would have 1 policy, which would give you 1 reward at every other step. So the expected reward is going to be half in that case. If you choose an action B with probability P, you will get reward every step. So that is 1 minus P, you would get 0. So you have 2 choices essentially. If you choose an action A, you get expected average of half. You choose B, you get expected average of P, right? And now I suppose you could see what is the problem with this kind of reduction, right? For any value of P greater than 1/2, you would find this reduction as an action B to be optimal, where we could clearly see A is optimal, right? What went wrong? What went wrong is the way that we have provided these rewards. So we have come up with a way to fix that situation. In particular, we provided a way to, give a reward in a way that is full and easy to compute, right? So the key idea is the following. I will quickly talk about this idea and then we can go to the next part. So the key idea here is that from every accepting transition, you can make a transition with probability 1 minus zeta to a sync state, right? And with the remaining probability, you would continue to do what you were doing earlier, right? And if you can do the same thing from every state, now you have a different problem of solved, right? But interesting part here is that you have the sync state. Any policy that maximizes the probability of reaching that sync state has a very interesting relationship with respect to optimal, probability for your programming language. So the key idea here is that for every system, for any value of zeta, if you can satisfy your, specification with probability 1, you could use any value of zeta, and whatever optimal reachability policy would be, that would also maximize your original specification. And in particular, for those cases where you cannot satisfy your specification with probability 1, you would get slight over approximation, but that over approximation could be tuned down as you would select the value of zeta, right? Here, roughly, I could show you quickly the idea here, right? So you have, like, for every accepting, end component, you would see that here the probability of satisfaction of your logical objective is 1. And you would see, especially on the other part, the probability of reaching that sync is also 1 from every state, because there is only one way to leak out of it, and that is through this accepting transition, right? So no matter what is the value of zeta, you would satisfy reachability with probability 1. Similarly, you could see if you are in the end component, rejecting end component, that is this portion of the graph where you have no accepting transition, of course, you won't satisfy your LTL or logical objective with any probability. And similarly, the probability of reaching sync is also 0 in the other case. And you would get from the transients, you would get some over approximation, but that over approximation could be tuned down as zeta goes to 1. Okay, so this kind of approach could be nicely integrated within the workflow of reinforcement learning. The key idea here is that your interpreter would simulate going to this sync by tossing this zeta biased coin. And every time this kind of comes to the head, the episode would get stopped, mimicking that you have reached the sync state. We have implemented this approach in a tool that we have been developing from last 4 years now, right? And this tool is MongoJerry. It's a formal reinforcement learning tool that provides, the interface of a Markov decision process as this, logic for writing this probabilistic program. This Prism language. You could write your specifications here in a well-established language, HOA, or you could also provide logical specifications directly, right? And then our tool provides this open AI gym-esque interface, between the interpreter and the reinforcement learning agent in such a way that you could use arbitrary, off-the-shelf reinforcement learning algorithm to connect with this idea. We have been collecting a lot of benchmarks since then, in particular, a lot of interesting. So you may see that maybe the example that I have given is slightly, peculiar, but then there are a lot of exciting protocols and problems could be reduced to that particular logical fragment. In particular, it has been quite popular in communities like control theory and formal methods from last 40 years and so, right? Going forward, so this is kind of, I have talked about really how, like an overall idea of how to introduce a very simple language and provide automatically rewards, but there are multiple directions to continue this work. And we have been looking into some really exciting directions here, right? So you may see, for example, one of the key problems in reinforcement learning is that of sparseness of rewards, right? It's particularly true when you have automata-based rewards in this case, right? So we are looking into kind of come up with better reward schemes. How do we go from automata to rewards so that it's kind of easy to learn, right? We have been looking into ideas like reward shaping or automata-based reward shaping, right? How do we exploit this automaton object to make rewards more dense? We are also looking around this, going beyond. We are going beyond, standard discounted reinforcement learning to average reward reinforcement learning. That seems to be particularly, easy for continual reinforcement learning tasks. We are also looking into another facet of that, which is like if you have multiple players interacting in the environment, right? So we looked into this idea of stochastic parity games. That seems to be a very challenging problem in computer science. In particular, it is one of those problems which is known to be in NP and co-NP and not known to be in polynomial time solvable, right? What we have done here is we have taken stochastic parity games and provided, rewards so that reinforcement learning could be used to compute optimal policies. Similarly, you could provide multiple objectives, not only single specification, but sequence of specification, right? And it gets really, really more challenging when you have multiple specification and kind of a certain order over that. And doing that automatically is really, powerful. Another direction we have been investigating is looking into richer models. So far you have seen, finite state Markov decision process. These systems could be continuous space as well, right? And some of our work that kind of takes some assumptions on the continuity of the environment to lift convergence proofs for such models. We looked into probabilistic time systems that provide like a nice structured, constraints on the environment. And there is some interesting idea on continuous time Markov decision process environments and formal specifications. Finally, I would kind of slightly talk about quickly this part where you want to go beyond this simple LTL kind of property, right? So we have investigated two directions. The first one, where you have your specifications are timed in nature, right? So we have looked into this language of duration calculus. That's like a most expressive language to express properties of, timed sequence of things. We have been looking into context-free reward languages. As you could see, like standard languages that we have seen so far, they are roughly connected to regular languages. And how do we kind of push that more in taking more richer specifications? Okay, that brings us to the second part. If I have any questions on the chat, I will take that here. Okay, any questions? Okay. In the second part, we would talk about this scalability challenge. In particular, how do we extend reinforcement learning so that it could kind of directly reason with programmatic abstractions like, program calls or stacks and so on, right? So this particular approach I would talk about is called recursive reinforcement learning, right? And that kind of generalizes your reinforcement learning or converges guarantees from finite state MDPs to recursive MDPs. Here is a quick example that kind of quickly motivates you to see why recursion is an interesting feature, or why you want to sometimes reason with infinite state MDPs, right? So here kind of it's like a interesting cloud computing scenario example. You are given a task that you could either monolithically execute on some server that takes certain time unit, or you could decompose into 3 different parts, right? Once you decompose into smaller problems, you could take each of that problem and, for example, you could choose either I would run it on some kind of a unreliable server, which is quite quick, quite fast, but with some probability, that may crash and I have to run that program again, right? Or you could run it on some other server, which is slightly slow, right? But more reliable. On the other hand, that particular task could be interrupted when you get a higher priority task, right? And that priority task could itself be interrupted when a higher priority task comes and so on, right? So interesting thing I want you to notice here is that number of states in these systems, they are unrestricted now, because you could have arbitrarily many processes present in the system. And in particular, if it is not known to you what are the different probabilities, how do you compute what is the optimal sequence of actions to use in that case, right? Sorry about that. So in particular, this problem could be reduced to writing this nice like stochastic context-free grammar kind of equations, right? Let's see what is happening over here. For process T, if you choose an action A1, you could kind of spawn 3 different processes of type S, or if you choose some other action, you could execute that in single step, and you are given some of the rewards for those, right? These classes of systems are known as branching Markov decision processes. And there is a nice history. They have been studied from a long time. In particular, they were initially proposed as branching processes to understand why certain aristocratic surnames, they go extinct, right? More recently, Atesami and Yanakakis, they have started looking into these models from an optimization point of view. So let's understand this stochastic context-free grammar better and see where we could use that in reinforcement learning. So another way to kind of consider the same sequence of rules is going to be this MDP-like, graph here. It's like your Markov decision process, but you have this strange kind of a branching transitions as well. You have normal determinism, you have stochasticity, but you have branching as well. The idea here is if you are in this particular process, choose an action A, you would branch into 3 different copies, right? And essentially, if you kind of quickly think about it, there is like a whole corresponding infinite state Markov decision process for that. So here we are interested in the following problem. We are given this branching Markov decision process, right? And we want to compute what is the minimum total cost to termination and compute an optimal policy, right? When the model is known, right? And in particular, when you have all of the rewards, which are strictly positive, time in our case, really, right? You could reduce that to a nice set of linear, nice set of constraints or Bellman optimality-like equations, right? And those could be solved using linear programming. On the other hand, when model is not known, it's quite kind of, there are a lot of challenges essentially. So in particular, what do I mean when I say model is not known? You know that these different processes in the system, but you have no idea about how are the branchings going on, how many processes can be evolved. They could be stochastic as well, right? So you do not know any of the probabilities, you do not know number of branches and so on. Now, hopefully, I would like to kind of quickly convince you what are the key challenges over here, right? The first one is that state space of the underlying Markov decision process is now infinite. That's one challenge. Second one is one-step reward is unbounded. The last one is because we have undiscounted rewards, there is no contraction. These are precisely 3 properties that make reinforcement learning work. We don't have them here, right? On the other hand, still there is a lot of regularity in this particular context. So what we did is we kind of exploited that regularity, in particular those optimality equations that we saw earlier, to provide a Q-learning algorithm with a guaranteed convergence towards the optimal value. Going forward, we have been looking into kind of extending this idea of branching Markov decision process to what is known as this recursive Markov decision process, right? We'll try to understand how are those models, but in particular, these systems, recursive MDPs, they could model your probabilistic push-down systems. Think of a probabilistic system with a stack with that, right? You could write context-free specifications in your reinforcement learning, right? For instance, in your, frozen lake example, if you want to say, I want to reach my final state, but I want to make sure that I am kind of charging and discharging locations, I'm being same number of time and so on, right? Okay, so you could, then we have looked into, the modular reinforcement learning also could be reduced to this particular model. I just quickly kind of go over that. We are given this, Boolean program that could be compiled into your recursive Markov decision process. These are like finitely many components. Each component is an MDP, but in addition to that, it could call other components recursively, right? So in particular, from the first component, you can call component S. From there, you could call component H, and from the component H, you can call itself without any bound, right? So we have looked into this more general class of Markov decision process and provided convergence guarantees for a tabular reinforcement learning with certain restrictions. For multi-exit RMDPs, deterministic multi-exit RMDPs, and single exit arbitrary recursive MDPs. In particular, for the general case, we have provided this nice reduction to this continuous state space. And using that, we have provided this deep reinforcement learning algorithm for that, right? And using this idea, you could, using this notion of, the environment and the structure, you could scale reinforcement learning algorithm more than it was possible earlier. All of these ideas, they have been implemented inside the tool, MongoJerry. And if you are interested in kind of extending this work, we are looking for students to work on that. Okay, so just quickly check how much time I have, 5 minutes or 10, okay? I will quickly talk about the last part of this talk, where we are looking into this next generation cardiac pacemaker. What is the role of reinforcement learning in developing safety critical systems, right? I have been working with John Comp from last 4 years. John Comp has been working with Medtronic from last 30 years, and he has been developing medical devices. In particular, he specializes in developing cardiac pacemakers. And we have been looking into, so cardiac pacemaker, if you haven't seen that, it's like a small device when your heart has some kind of a block, right? It kind of provides electric signals to that so as to make sure that heart is doing the right thing it's supposed to do. Pacemakers, they have been kind of, have been around since 1950s, and they are getting more and more miniaturized. They are getting more and more smarter. And hence in medical device industry, there is intense pressure to come up with clever ideas, clever design for such systems. So we proposed as a first idea of reinforcement learning, we suggested that as a creative design space exploration idea, right? So you want to come up with a pacemaker using this creative power of reinforcement learning. We developed these two kind of extensions of duration calculus logic, or restriction of duration calculus, called time triggered and event triggered. John has been looking into coming up with the requirements of VVI and DDD. They are two different kind of pacemaker families, really, right? He studied those and kind of captured those inside this formal logic, right? So I'm showing here this simpler VVI pacemaker, but DDD pacemaker is kind of something much more complex. Then we provided a way to take this logic exactly in the same way as we have seen before to automatically convert those to rewards. And now reinforcement learning could be used to kind of get reward from this logical specification. But in addition to that, coming up with a non-deterministic, a creative solution to solve the same problem. Of course, there are no guarantees of the correctness, and you would like to use, formal verification to provide guarantees about such pacemaker as you would do even with the manual pacemakers. Another direction we looked into is like reinforcement learning for adaptive cardiac pacemaker. It's a kind of a very interesting idea, right? So here I'm kind of quickly talking about this interesting situation that you can get sometime with the heart block. It's called 3-2 heart block, right? What happens there is that every third beat is missing. So you would get something like boom, boom, space, boom, boom, space, right? And you could use pacemakers. It's a well-known, therapy exactly for solving that problem. And pacemaker comes and finds the missing beat essentially, right? So it provides, if it doesn't sense the ventricle pacing, it provides its own pace over there. Here is the problem with the current pacemakers, right? You could see, I suppose, here, right? So for example, if your heart is going with, certain rhythm, current pacemakers, they always go and deterministically pace at some time unit. They're not listening to your heart. It goes like this, boom, 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 right? And patients, they could often, sense something is wrong with this kind of pacemaker. Wouldn't it be nice if we could embed reinforcement learning inside such pacemaker, such that they're always correct and always learning and adapting, right? Here is this idea really. We identified a fragment of DC called safety DC. From that, we have synthesized a shield around the pacemaker, right? That overrides all of the pacemaker actions if they're not correct, right? So if you think about it, even if it is not learning anything, it's always correct, right? And then in addition to that, you could now use reinforcement learning paradigm to come up with an optimal behavior there. Using this and in our kind of proof of concept, we have shown that it kind of performs better than state-of-the-art pacemakers. by kind of trying to get closer and closer to the rhythm of the heart and kind of modifies according to that. Also, currently we are looking into kind of power requirements and memory requirements of squeezing down the strategy that we have right now. Finally, I'll touch upon some of the direction that we have been looking into that were not covered today. We have been doing some really exciting work on security critical systems, in particular security for cyber physical systems, for software security, right? And in particular, I want to kind of shout out to Tian Han, who recently got this exciting award on his work on, static analysis for availability attacks. Another direction I've been looking into is kind of understanding different notions of fairness in neural networks, right? And in particular, from the software engineering point of view, right? We are looking into how to help software engineers to develop this fairness-aware configuration of ML libraries. If you're a software engineer, you are using some particular library, right? You want to know that what parameters I should use so that it is not kind of aggravating the unfair or discrimination inside the system. Finally, I will just take one more minute on talking about accountability. This is some really exciting work which I have been doing recently, right? And it's about how do we help, software engineers to debug the tax preparation software system, right? Let's see what is going on. If you're like me, you do not remember when is the last time we filled the taxes manually, right? They are getting more and more complicated every year. You get Bitcoin, it gets more complicated. You get some other coin, so they are getting extremely complicated. Now, 80% of us, we use software to, file these things. It's nice. And then every time you go and say TurboTax, what's the rate for that? If there are any open source analog for that, I could use quickly, right? Or there are many softwares that come out with this. This is quite nice. But then these softwares, they could have bugs inside as well, right? And if there is a bug in the software and you file if you get, if you file and you have a buggy software, whose mistake is this that you have been using a buggy software, right? Any guesses? Yours, it's your mistake, right? You can get money back from TurboTax. But once you get audited, you cannot kind of blame the software for your errors, right? So we have been looking into kind of finding the role of formal specification and kind of automatic, testing and verification of such legal critical software system. The key challenge in this case is that there is no oracle. You do not know for a particular user what should be the tax return in that case, right? Every user is different and it's very expensive. We pay people to exactly solve that problem. There are other challenges also, but the first one is really big one. And for that reason, we do not know how do we come up with the specification. What is a good specification, right? For a particular user, what is the value we should get, right? On the positive side, the US law is based on the common law system, right? And common law system is based on this particular tenet, right? What is that? It's called stare decisis, right? Similar cases must follow similar rulings. And that kind of gives a quite interesting hint towards, verification of finding the specification for such systems. What is that? You get this corollary, right? Correctness properties for legal software can be defined in terms of relating similar cases. You would say, I do not know what this particular user is going to get. But then if two users are really close to each other, but only differing in that, the output, I know exactly what that should be. And interestingly enough, all of our specification for IRS specifications for taxes, they are all of that kind. So we worked with a couple of people who know what they're talking about, like, Christia Reed JD, right? And we looked into this, IRS manual of, rules for that particular year, right? It was like last year, I think we did that. And we extracted a bunch of this specification, and all of them, they have this notion of metamorphic specification. They are like relating different cases, right? And after extracting those specifications, we developed this whole software framework that looks into IRS document. We got the specification from that. We got this formal kind of properties of that. And we use this open text solver software that is like one of the leading open source free text filing software available to us, right? And in particular, using this idea, we found 4 different, bugs inside the system. We have been talking to open text solver people, and this year they have removed some of those problems, but they have introduced a new set of problems as well, right? So don't use that if you're thinking of using. That finishes my talk. Here is acknowledgement for the funding to all of these agencies, and special thanks to my collaborators and the students. Thank you. Yeah. Questions about, filing your taxes, maybe.
Maybe that we start with the question. So when you talk about programmatic reinforcement learning, right? So what we expect is like a programming language or some sort of way to to translate something that's human programmable. But you went straight to logic, and we all know that logic is not exactly the paradigm for something that humans can easily write. So I wonder what are you going to do about that, right?
Right. So what I talked about today is essentially the foundation for those algorithms that would work on such a software. We are looking into like making reinforcement learning as easy as writing Python, right? So we are integrating in Python programs those holes and kind of connect that in the background to reinforcement learning that is of the form, recursive reinforcement learning. You may think of this framework to be similar as what SLAM used to do in the past, right? So it's essentially Bebop version. The recursive reinforcement learning is that kind of version for, right? So it's like you would take initial program, you would abstract it into something that would have recursive structures inside, and the algorithm proposed could work with that. So we still have to do a lot of work with respect to interface of these algorithms. But I hope that kind of connects, at least from the recursive reinforcement learning side. But yes, we are kind of pushing in that direction to kind of work with arbitrary software specifications and environments. Evan, it's a home question, yeah.
Yeah, so maybe it's a little bit along the lines of what you just asked, but like, if you're now thinking about refining like your undergrad, you're like your CS1 and CS2 with like reinforcement learning based programming, how would you think about like what would be your step? What's kind of different about that program?
Yeah, so we have recently received some funding in integrating reinforcement learning with using that to teach children how to program, right? So in particular, it kind of elevates the interface that you would have with the programming system. So far, when we program, we kind of say exactly what we would like to do and how, right? But wouldn't it be nice where you could say, you write a partial program and you say, I do not know how to write this program, but this is the property I want to, my program to satisfy. And it's like brings your, interaction with your programming or compiler at a higher level, where you could just write the sketch of the program and add the specification, and your compilation, which would be a reinforcement learning agent that would, spit out the program for you. So yeah, I'm thinking of kind of using in that direction, and we are looking into some of the simple programming languages to kind of adapt that there. Yeah.
So I was interested when both at the beginning and then in the medical device space, you said RL is, or like machine learning can be used for creativity, because for the most part, that's actually pretty open and pretty ill-posed.
Yeah, yeah.
And then you did mention that you're doing that for medical devices, and I get that you have properties to check, but for goodness of the invention or creativity of the invention, do you have a human in the loop, or what's your evaluation?
Right. So currently what we are doing is like in the design space exploration part, right? So we are not suggesting that we should use that pacemaker, right? On the other hand, for the second version, where we have this, the adaptive pacemaker algorithm, right? That is as good as the algorithm that you would get otherwise, right? In particular, I would suggest really, right, that it's like the second one, you don't even have to verify if this is the specification that you have in mind, right? So you have like a rigorous set of specification that you would, take your standard pacemakers and then verify those properties. In addition to that, you validate, right? So we are kind of asking both of the steps for this as well. But again, for the adaptive system, because, reinforcement learning agent comes already, with the shield around it, right? It does satisfy the kind of specification that we kind of tend to verify. But again, yeah, it's a valid question really, right? So we still need to, so what I'm thinking of is the proper paradigm would be like a human written code, but interesting parts left out for reinforcement learning agent to fill. So it has like a beauty of both. You could read the code, but then you can kind of adapt to certain parts of the program as well, and then validate that. That makes sense? I mean, this is a really challenging problem, right? Safety critical systems using reinforcement learning is, I mean, if you would ask me 5 years back, I would say, don't do it, right? But then people are doing it anyway, right? So what we are doing right now is coming up with a case for how you could do it more systematically.
Okay. So I think we are just about out of time. So let's thank the speaker one more time. I don't quite buy the shield argument. There's a catch there, right?